So we want to go back and look at the bladder again. So again, in men, the bladder sits in the pelvic cavity, anterior to the rectum, and then above the prostate gland that is below it. In women, the bladder is still anterior to the rectum, but it's also anterior to the vagina, and the uterus overlies it, and so the bladder is here. So if you look at these models of the bladder, it looks like this lining is folded, and it looks like the lining is folded here. So if we look at this model, and we pull this model open so we can actually see the bladder itself, then we'll notice that there are considerable folding patterns to the lining of the bladder. So the stomach and bladder are both hollow organs that fill with a substance that stretches them. And so they're both organs that have rugae or rugae. So these folds would be much smaller when the bladder is extended and much more pronounced when the bladder is not extended with urine. So when we're looking at the wall of the bladder, we have a muscle that we can see histologically that would make up the wall of the bladder to the outside edge here. And like the stomach, it has 3 layers of smooth muscle. Now in the stomach, because the stomach needs to churn, we had an inner oblique layer, a circular layer, and a longitudinal layer. The smooth muscle in the bladder contracts the bladder, which provides forced urine flow for us. And if you haven't seen that, then when you change the diaper of a little baby boy and you forget that they go whenever they want, and you get this giant fountain because of this muscle layer that's pushing the urine out. So in a bladder, it's inner longitudinal, circular, and outer longitudinal. So instead of having an oblique layer that allows it to churn, we just have layers that compress the bladder to force urine out of it. Now if we look at where the ureters enter the bladder, so on the backside here and here, on the inside that would be this opening here, and this opening here would be the opening. Notice that it's at the top of a white thing that looks triangular, and the opening to the urethra would be down here. So this white area is called the trigon, and it's defined by the left and right ureter openings, and then the urethral opening. Notice that this layer does not have rugae, because rugae would trap urine behind it. So the trigon is an area that's triangular shaped, and it's smooth so that we can void all the urine out of this area. So urine will be gone from this area. So trigon, triangular shaped, urine is gone from it. And then again, where the urethra exits through the wall of the bladder, we have a sphincter here, which would be our internal urethral sphincter. So this muscle that forms the wall of the bladder is called the detrusor muscle. So the wall of the bladder has a detrusor muscle, and then where the urethra passes through that, we call that the internal urethral sphincter. And then because the bladder sits in the pelvic cavity, then the bladder on the surface, particularly in men, is covered by a visceral peritoneum. In women, only the anterior aspect of the bladder is covered by visceral peritoneum, because the visceral peritoneum goes over the uterus and then drops down on the bladder, and it doesn't occur between the uterus and the bladder itself. So the last thing we want to cover is blood supply. So obviously the kidney is the only area in the body where we truly filter blood to get rid of waste products through our urine. So we have to bring blood to be filtered and then drain it. So blood to the kidney are branches off the aorta called renal arteries. Now the pattern we're going to see is that as we branch, we rename an artery, and we're going to get to smaller and smaller branches so that eventually we can get to all those Bowman's capsules or glomerular corpuscles. So what we're going to do is the first branches off of this renal artery here are called segmental arteries. And then branches off the segmental arteries that pass through renal columns are called interlobar arteries. Now, as interlobar arteries enter the cortex, they run along the surface of the renal pyramid, and so these that run along the surface are actually arcing along the pyramid, so they're called arcuate arteries. And then branches off the arcuate arteries going out into the cortex are referred to as interlobular arteries. So the way to think about a kidney is that this artery that's feeding this entire area is feeding a lobe, so interlobar. This artery that's feeding a subset of the area that this artery goes to is feeding a lobule, so it's interlobular. And then the drainage pattern is the same. So what drains the structures in the cortex are interlobular veins. Interlobular veins feed into these veins arcing across the top of the pyramid here, so arcuate veins. Arcuate veins pass through columns, so interlobular veins. And then interlobular veins are going to come together to form these branches that we're seeing right here. Now here's a discrepancy in anatomy. So for much of modern anatomy, these were called segmental arteries and segmental veins. But just in the last couple of editions of textbooks, they have dropped segmental veins and basically say now that segmental veins don't exist. What you'll notice in my lab and in my lecture stuff, I've retained segmental veins just so there's symmetry for students, so that you know that if this is a segmental artery, what's sitting next to it is a segmental vein. And then if somebody ever asks you, you can say, yeah, he said that in recent editions, segmental veins have been dropped. So you know. And then this was a renal vein that would go to the vena cava. So this is an old model of the kidney. So our reference point is that this would be toward the center of the kidney below these two blood vessels going this way. So this would be the medulla. So above these two blood vessels up here would be the cortex. And the cortex is easy because it has the renal corpuscles, the little green balls. So if you recall, when we were just doing blood vessels, the blood vessels that were arcing across the interface between the medulla and the cortex were arcuate arteries. So this is an arcuate artery. And so the artery that comes off an arcuate artery and goes up into the cortex is an interlobular artery. The branches off the interlobular artery that go to the renal corpuscle are afferent arterioles. And then what drains the glomerulus inside the renal corpuscle here is this blood vessel, which is a efferent arteriole. So now if we look at this pattern over here, then here's the arcuate artery, here's the interlobular artery. So this is a afferent arteriole, and this is a efferent arteriole. And notice the efferent arteriole goes to a capillary bed that's overlying the tubes in the kidney. So this is called a peritubular capillary bed. So to make sense out of that, then if we look at one of these nephrons, and so let's start with this nephron, then notice that what's connected to the pink ball is this salmon colored stuff, and it's all folded. So this is our proximal convoluted tubule. And then the proximal convoluted tubule leads to this really long thing called a loop of Henle. So here's the descending limb of Henle, and the thick part is up here, and the thin part is the purple. Here's the loop at the bottom, and here's the ascending limb of Henle. And then notice it becomes thick here, so thin ascending limb and thick ascending limb. As we go upward, Here's where it converts to the distal convolute tubule. Here's where the distal convolute tubule is lying next to our blood supply, our afferent arterial and our efferent arterial. So this is the juxtaglomerular apparatus we were just talking about. And then the distal convolute tubule is this purple folding, leads into a collecting duct, and then the yellow is a collecting duct that leads all the way down into a papillary duct. So what's kind of cool is the color pattern here. They made the collecting duct yellow and the papillary duct yellow, largely because we've pretty much made urine at that point. So it's yellow because it's largely urine. Where things are still being processed, the proximal convoluted tubule and distal convoluted tubule and the loop of Henle are done differently. So this, remember, is a renal corpuscle sitting next to the medulla. It's got a really long loop of Henle. So this is a juxtamedullary nephron. If we look at this one, here's a renal corpuscle way up in the cortex and a very short loop of Henle. So this is a cortical nephron that's being depicted here. Notice that this efferent arterial from this juxtamedullary nephron runs down, then we have a capillary bed down here. This is a unique vascular system that's unique to juxtamedullary nephrons, so it's called a vasa recta. So the one we have up here is a peritubular capillary, and the one we have down here is a vasa recta. So again, your landmark are these, which are arcuate arteries and veins that separate the cortex up here from the medulla down here while you're looking at that model. So if we exit the capillary tubule, the peritubular capillary here, then the blood flows into an interlobular vein that drains from the cortex and enters an arcuate vein that we're seeing right here. And also notice that this vasa recta is drained into the arcuate vein as well. So that includes everything for Lab 1 for Unit 2, which is the urinary system.